Okay, this is going to be the second video on how to sketch complete graphs using calculus techniques. And in the first video, we had f of x, and it was equal to a polynomial. So when we had a polynomial, there were no asymptotes. Now, in this second video, we'll look at a rational function that does involve asymptotes, and that changes how you go about things just a little bit. Now, if you haven't done it yet, I would definitely suggest watch the first video first, because it will describe how what the steps were involved and how we went about sketching it. And I think it'll make a little bit more sense when you watch this one. But we'll go ahead and run through this just like we did on the last video. Now, there were 11 steps altogether. We're going to follow those same 11 steps this time, and we'll use the same process. So first of all, you'll have a worksheet in front of you. This is the page that you're going to do all the work on. Then you'll have a graph, and we'll go to a blank graph, and it looks like this. So you actually should have two things in front of you before you start. Now, just like we did the last time, the whole process will involve taking first derivative information, and the first derivative information will be used for things like increasing and decreasing critical points, maximums and minimums. Then we'll also use second derivative information, and that will be used for inflection points, concavity, and whether it's concave up or concave down. And then in this thing, we'll also introduce asymptotes, and they affect the behavior of the graph a little bit too. But just like in that last one, we'll put all our first derivative information stuff at the top of the graph. So I think just like in the first video, what I usually do is in blue, I'll put all the first derivative stuff. So at the top of the graph in blue, I'm just going to write first derivative up here. So everything at the top of the graph will involve information from the first derivative. And that will all be in blue. Then at the bottom of the graph, on the second derivative, we'll put all the second derivative information down here. And we'll put that in red. So we'll make this be the second derivative. So the second derivative, and again, this is exactly like what we did in that first video. So hopefully you've watched that. So first derivative information in blue at the top of the graph, second derivative information in red at the bottom of the graph. So that'll give us a good start. Now, the next thing we're going to do is this. Let's go back to our steps and we'll look at the process. So the function we're given to work with is a rational function, x squared plus 1 divided by x squared minus 2. Now, in that last video, the first step is to sketch any vertical or horizontal asymptotes. But when you're dealing with polynomials, we didn't have any horizontal or vertical asymptotes. So on that first step, we just put none and bypassed the first step and started with the second step. But in this case, you're actually going to get quite a bit of information because this is a rational function. So we want to sketch the vertical and the horizontal asymptotes. So let's work on the vertical one first, and we'll put that over here. So we want the vertical asymptote. Now, the vertical asymptote is going to occur wherever the denominator is equal to 0, which makes the whole function undefined. So to find the vertical asymptote, set the denominator equal to 0 and solve for x. So that's going to give you x squared is equal to 2. So x would be equal to plus or minus the square root of 2. Now, because we're going to graph this, go ahead and change that square root into a decimal. So I'll make that be plus or minus, and the square root of 2 would be 1.4. So what this is going to be, those are going to be my vertical asymptotes. Now, just like we did in the last thing, every time we find something, we'll go ahead and put it on the graph. So now we know where the vertical asymptotes are, plus or minus 1.4. So let's go to the graph. And the only thing that'll be a little bit different is this. All the asymptote information we'll go ahead and put in green. So at minus 1.4, about right here, I've got a vertical asymptote, which is going to divide the graph up into intervals. So I'm going to draw a vertical line right at 1.4. So from here, and it'll go down, say, to about right here. So there's the first vertical asymptote. And I've got another one over here at 1.4, so I'll do the same thing here, is divide the graph up into intervals, but 1.4 from here, say, down to about right here. So there's the second one. So that actually divides it up into 3 intervals. So 2 vertical asymptotes. So now let's go back to the worksheet, and on the worksheet, now we want the horizontal asymptotes. So to find the horizontal asymptotes, this is going to, since it's a rational function, this is like finding the limit as you go way off to the right or way off to the left. So in effect, you're really doing this. You're finding the limit as x approaches, if we go way off to the left, a negative infinity of this function right here. So we've got x squared plus 1 over x squared minus 2. Now, you might remember from your limit rules as you let x approach infinity, if the power in the numerator is the same as the power in the denominator, the limit will actually be just the ratio of the leading coefficients. So in this case, it's going to be these coefficients right here, 1 over 1. So this will turn into 1 divided by 1, which is 1. And what this means is, as you go way off to the left, you'll have a horizontal asymptote approaches the line y is equal to 1. Now, we'll take a look at it going way off to the right. So as x approaches a positive infinity, and actually you've got the same thing. It'll be 1 x squared plus 1 and 1 x squared minus 2. And you can use exactly the same argument because the power in the numerator is the same as the power in the denominator. The ratio will be the leading coefficients, 1 over 1, which is 1. So again, going off to the right, it's the same horizontal asymptote, y is equal to 1. So what this means is horizontal asymptote in this case is going to be a horizontal line through y is equal to 1. So let's go ahead and sketch that one. So we'll go back to the graph, and again, we'll put all the asymptote information in green. So what I want here is y is equal to 1, and I'm just going to go ahead and put a horizontal line all the way across the page at y is equal to 1. So it will look something like that. So I've got the 3 asymptotes on there. So that takes care of step 1. You've got it set up. Now let's go back to the remaining steps. Okay, the next thing to do is to find the y-intercept and the x-intercept. And to find the y-intercept, of course, set x equal to 0 and solve for y. So you would have y would be equal to, this is going to be the y-intercept. So to find the y-intercept, everywhere you've got an x, just replace it with a 0. So plus 1 divided by 0 squared minus 2. And when you do this, of course, that'll go to 0, and you're left with negative 1/2. So the y-intercept is a negative 1/2. So there's the y-intercept is a negative 1/2. And let's go ahead and plot that on the graph. So again, I'll go back to the graph. And this is going to be the first actual point on the graph. So I'm going to go ahead and put that in, and we'll put it in right here. So this will be in, I think I'll put this in blue. So at minus 1/2, the first actual point on the graph that we've got is right there. So there's our first point. And that's going to be the y-intercept. Now let's check for x-intercepts. So we'll go back to the work, and this time checking for the x-intercept. Now, to find the x-intercept, set y equal to 0 and solve for x. So you'd actually have this. In place of y, put a 0 is equal to x squared plus 1 divided by x squared minus 2. Now, to solve this, what you've got is a fraction is equal to 0. The only way that a fraction can be equal to 0 is if the numerator is equal to 0. So for all practical purposes, you can forget about the denominator. So what this means is 0 has to be equal to x squared plus 1. Now solve this for x. Well, you'd have minus 1 is equal to x squared. And what this tells you is this: no number squared will ever equal to negative 1, so that is never true. So in this particular case, since it's never true, what that means is there are no x-intercepts. So no x-intercepts. Now that won't be the case in every problem, but it is in this case right here. So back to our graph, if we take a quick look at the graph, that just means that there's no additional points out of this step because this graph will never cross the x-axis. So we go ahead and just continue the additional steps in trying to build up other information. So let's go down to this. Now the next thing you're going to need before you get finished, you're going to need the first and second derivatives. So my suggestion is just early in the problem, go ahead and find the first derivative and find the second derivative. So first of all, let's find the first derivative. So I think I'll put that right here, and we'll do this in black. So I want to find the first derivative. So f prime of x. Now to find the first derivative, if this is the original function, you're going to have to use the quotient rule. So what the quotient rule says is that the derivative is equal to, and I think I'll put a bar right across here. So we'll go from here over, say, to about right here. It's going to be equal to the denominator. So I'll have x squared minus 2, then times the derivative of the numerator, but that would be 2x. So I've got a 2x. Then minus the numerator, which is x squared plus 1, times the derivative of the denominator, which would be 2x, all divided by the denominator, which is x squared minus 2, the denominator squared. Okay, now solve this thing. So what we'll do, first of all, is go ahead and distribute this 2x, and then we'll distribute this 2x. So x squared times 2x, and again, we'll put a bar right across this whole thing. So it'll look something along this line. So x squared times 2x would be a 2x cubed. Then minus this times this would be minus 4x. Then on this one, when you distribute this times this would be 2x cubed, but it's going to be negative. So minus 2x cubed. And finally, 2x times 1 would be 2x, but it's going to be negative, so minus 2x. All divided by, this is going to be x squared minus 2 squared. Now, if you look at this, you've got a positive 2x cubed and a negative 2x cubed. These two will cancel out. So the final first derivative will wind up just being this. It's going to be minus 4 minus 2 would be minus 6x divided by x squared minus 2 squared. And that's going to be the first derivative. So we've got the first derivative figured out. And I'll go ahead and just put a little box around that just to isolate it. So there is the first derivative. Okay, now we'll need the second derivative. Well, what the second derivative is, it's just going to be the derivative of the first derivative, so let's go ahead and find that. So I want to find this time f prime prime of x. And again, it's just the derivative of this thing, but this is also the quotient rule. So again, we'll write the whole thing out. It'll look like this. It's going to be the denominator. So the denominator would be x squared minus 2 squared times the derivative of the numerator, which would be negative 6, then minus the numerator, which would be negative 6x, times the derivative of the denominator, but in this case, we'll extend this out just a little bit. That's going to involve the chain rule. So the derivative of the denominator, first of all, you'll have the derivative of the outer part, then rewrite this original inner part, times the derivative of the inner part, which would be 2x, and using the chain rule, that'll be the derivative of the denominator. Then all divided by the denominator squared. So that's going to be, it would be x squared minus 2. Now if it was squared, when you square it, now it'll be to the 4th power. Now the next thing to make this a little bit easier, in this top one here, we went ahead and distributed right away and then canceled things out. When you're working with the second derivative, it's a little algebra trick here. There's a way to make this easier. Rather than distributing and foiling this whole thing out, you'll wind up with a really complicated numerator. So a trick is to try to factor out anything that they have in common. Now notice, here is a x squared minus 2, and here is an x squared minus 2. So I can factor an x squared minus 2 out of that part of the numerator. So that's what I'm going to do next. I'm going to go from here, and I'll go ahead and write this whole thing out again. It'll be something about like that. So first of all, since both those have an x squared minus 2, I'm going to go ahead and factor out an x squared minus 2. Then what would be left over would be this. Now here I had x squared minus 2 squared. When I factor out 1, I'll just be left with a single x squared minus 2. Then here's that negative 6. Then minus a minus 6x. Then, now again, I had an x squared minus 2, but I factor it out. So now I've just got 2 times 2 x. And I'll put a second set of brackets around that. So really all you did there, you just factored out an x squared minus 2. Now why would you do that? Because it makes the algebra a lot easier. So this is going to be x minus 2. So the next step I'll do is this. By factoring this out, it allows me to do this. I've got an x squared minus 2 in the top, and x squared minus 2 in the bottom. This one here will cancel out one of these here, and this is now cubed. So I just made the whole thing a little bit easier. So by factoring out first, it makes it a lot easier. So now the second derivative would be equal to, and we'll put a little bar across there. Now I'll go ahead, at this point, I'll go ahead and distribute this thing. So I'll distribute this negative 6. So this times this would give me a negative 6x squared. And then 2 negatives make a positive. That'll be plus 12. Then on this one, I've got actually 2 times 2 is 4 times 6 is 24. That'll make it, 2 negatives make it positive and x squared. So I'll wind up with a positive 24 x squared, all divided by x squared minus 2, whole thing cubed. Now again, we'll simplify this if we can, so we'll shorten that up a little bit and make this be, we can put all this together. So this is going to be, I've got a 24x squared minus 6x squared would be 18x squared plus 12, all divided by x squared minus 2 cubed. So what that's going to be, that's going to be the second derivative. So the second derivative would be this right here. So now I've got the first derivative and the second derivative. I'll go ahead and again put a little box around that one just to isolate it. And actually, that's probably the hardest part of this whole process, is finding the first and second derivatives. So now we've got those, and we'll use these two things to give us information about the graph. So with that out of the way, let's go down and see what the next thing is. Okay, the next thing would be this. Find the critical points on the graph. And to find the critical points occur where the first derivative is either equal to 0 or it's undefined. So we'll find the critical points and mark them on the graph. So to find out where they are, here is the first derivative right here. So we'll take the first derivative, and I'll move it up just a little bit here. Take the first derivative, set it equal to 0, solve for x, and that will tell me where the critical points are. So set the first derivative equal to 0. This is going to be 0 is equal to, and using this up here, the first derivative was minus 6x divided by x squared minus 2 squared. Now you're back to this thing again where if you've got a fraction equal to 0, the only way the fraction can be equal to 0 is if the numerator is equal to 0. So you can forget about the denominator and just set the numerator equal to 0. That's going to give you minus 6x. So solve that for x, and if you divide both sides by x, you'd really get this. You would get that x would have to be equal to 0. So what this is, x equals to 0, this is a critical point. And in this case, it's the only critical point that you get on this graph. So let's go ahead and plot that point on the graph. So we'll go back to our graph, and just like we've done before, all the first derivative stuff we'll put in blue. And now to find this, before I plot this thing, I need to do one more thing back here first. I know what the x value of it is 0, but to plot the point, I'll actually need a y value too. So I'll actually take this value of x at 0. And this is something we actually did in the first step, but we'll do it again one more time here. I know what the x value is. I want to know what the y value is. So take the original function and plug in the critical point. So the original function was x squared plus 1. So that's going to be 0 squared plus 1 divided by 0 squared minus 1. And again, the zeros cancel out, or minus 2, sorry. And that's going to give you a minus 1/2. So when x is equal to 0, y is equal to minus 1/2, and you get the point 0 minus 1/2, and that is a critical point. So you've got your first critical point. Now let's go ahead and plot that. So when you come over here to plot it, and again, we'll plot it in blue, it turns out we already have it. The y-intercept was -5, and the critical point turns out to be exactly the same point. So in this case, this will actually just take the time to label it, and we'll call it a CP right there. So you know that you have a critical point right here. It's equal to 0. And also, to help sketching the graph later on, I definitely would suggest whenever you have a critical point, go ahead and put a horizontal tangent. Put yourself a short tangent through there. And that's going to remind you as you sketch the graph to make sure the graph levels off and has a horizontal tangent at that point. So again, just a short thing right there. So if the first derivative is equal to 0, since the first derivative is the slope of the tangent line, then the tangent line has to have a horizontal tangent right there. Okay, so we've got the critical points. Now what that does, the next thing, let's go back to our thing here, says this. We mark the critical points on the graph, and that's going to divide the thing up into intervals. Now here's where it's going to get a little bit different than a graph that did not have asymptotes. Let's take a look at this. So first of all, we'll go back to the graph. Now, just like in that first example, everywhere you have a critical point, the graph could change from increasing to decreasing, so it'll mark a division of an interval. So I'm going to put a blue line right through this critical point, a blue vertical line. It's one of the intervals could be divided up right here. So we'll go to there. So what this means is this. Now, just like before, I want to mark intervals where it could change from increasing to decreasing. So when you work with this, now, strictly speaking, an asymptote is not a critical point, and it's also not an inflection point, because the critical points and the inflection points actually have to be points on the graph. Because the function's not defined at an asymptote, then there's not a point to plot. So strictly speaking, an asymptote is not a critical point or an inflection point. But here's the little caveat with that. You can treat it as if it behaves as if it is a critical point. In other words, the function could change from increasing to decreasing at an asymptote, just like it could change from increasing to decreasing at a critical point. So when we do this, we'll actually treat the asymptotes as if they behaved as if they were critical points. So what that means is when you mark your intervals up here now, we'll actually have this. We'll have one interval, say, that goes from way off at infinity to about right here. So that's going to be, here's the first interval. Now, at the asymptote, it's possible it could change to increasing and decreasing, so we'll treat that as a second interval. So a second interval goes from here to here. A third interval goes from here over to here. So you've got a third interval that goes like this. And you'll have a fourth interval that goes from here, and we'll say over to about right here. So the key when you're dividing up the intervals to sketch your graph is just to remember, you'll draw a vertical line everywhere you have a critical point, but you also treat the asymptotes, they behave as if they were critical points. So divide up the intervals on those two. So in this case, we get 4 intervals. Now, the next thing we're going to try to figure out is in each interval, is it increasing or decreasing? So back to the worksheet. Okay, we marked the corresponding intervals on the graph, and we included the asymptotes. So now, next point is, and you might remember, pick a test point inside each interval. So the idea is if you pick a test point where the first derivative, and you evaluate the first derivative, if the first derivative is positive, that means that the function is increasing. If the first derivative is negative, it means it's decreasing. So pick a convenient test point. So let's look back at the graph, and I've actually got 4 intervals now. Now again, I would suggest, again, pick a convenient test point, and that usually means an integer. So in each of these blue intervals, I need to pick a test point. In this case, I'm going to pick -2 in this first interval. I'll pick -1 in this second interval. I'll pick 1 in this third interval, and I'm going to pick 2 in this interval right here. Now, if you wanted to, you could pick 3 or 4, you could pick whatever. But I usually find it's easier to pick the most convenient one, which in most cases is going to be integers. So we're going to pick -2, -1, 1, and 2, and we'll evaluate the derivative at those points. This is going to be the first derivative test. And let's go back to the worksheet now. So over here, we need to do the following. We need to take the derivative, and we want to evaluate the first derivative at -2. We want to evaluate the first derivative at -1. we want to evaluate the first derivative at positive 1, and we want to evaluate the first derivative at 2. So those are going to be the intervals. Now, we'll do it the same way we did it in that first thing. All I'm interested in here is just, is it positive or negative? I don't particularly care about the number. Now, just a reminder, too, the actual function itself, the derivative, and we'll write this here one more time. The first derivative was, and we can look right back up here to find it. The first derivative was minus 6x divided by x squared minus 2 squared. So I'll write this just down here just so we have it. So minus 6x divided by x squared minus 2 squared. Now what you want to know is, when you plug in the test point, is the derivative positive or negative? So in this case, we would have minus 6 times minus 2 divided by, and in place of x, we'll put a minus 2 squared, minus 2, and the whole thing squared. Again, we're not particularly concerned about the numbers, so I'm going to do exactly like I did before, put pluses and minuses if I can. In the numerator, negative 6 times negative 2 is a positive 12, but all I care about is the fact that it is positive. Now, in the denominator, I'd have this. If I take negative 2 and square it, I'll get a 4. So that's going to be 4 minus 2 squared. So in the numerator's positive, if I take 4 minus 2, 2 squared would be 4. It's going to be a positive divided by a positive. The whole thing will be positive. And what that tells me is that this graph is increasing in this interval. So I've got my first interval. Now we'll do the same thing for the other intervals. This time I've got minus 6 and put a negative 1 in, divided by, this is going to be a negative 1 squared minus 2 squared. Well, in the numerator, negative times a negative will turn into a positive, divided by, now the same thing in the bottom. No matter what I have here, when I finally square it, it's going to turn out to be positive. So that's going to give me a positive divided by a positive, which would be a positive, which says that it must also be increasing in the second interval. So now let's go to the next interval. This time I'll plug in a 1. So I've got minus 6 times 1 divided by, this is going to be a plus 1 squared minus 2 squared. Now use the same logic. Negative 1 times 6 is going to be a negative in the numerator divided by, and no matter what you have in the denominator, when you square it, it's going to turn positive. So what you've got here is a positive divided by a negative, which will give you a negative, and that tells you that the function is decreasing. So again, you're not concerned about the numerical value. All you want is positive or negative. Finally, plug in a 2. So I've got minus 6 times 2 divided by, and I'll have 2 squared minus 2 squared. So again, negative 6 times 2 would give me a negative 12, but it just means a negative in the numerator. In the denominator, 4 minus 2 would be 2, but when I square it, it's going to become positive. That means that this is also going to be a negative. This is going to be a negative, and it's going to be decreasing. So it's going to be increasing in the first interval, increasing in the second interval, decreasing in the third interval, and decreasing in the fourth interval. So now, go back to your graph and write that information on the graph. And again, we'll do this in blue. So in the first interval, we found that it was increasing, so it's got to be increasing in this interval. It's got to be decreasing in this interval, increasing again in this interval. It's got to be decreasing in this interval, and it's got to be decreasing in this interval. So that's all the first derivative information stuff, and you've written it in blue at the top of the graph. So now, what about the second derivative information? Well, let's go back to the graph, probably back to the worksheet. Now, next thing to do is this. We'd like to know, we know where it's increasing or decreasing, and we'd like to know at the critical points, do they represent maximums, minimums, or neither? Well, just a reminder, what the first derivative test says is if you go from increasing to decreasing, you'd have a maximum. If you go from decreasing to increasing, you'd have a minimum. And if it doesn't change sign, if it doesn't go from increasing to decreasing, then you would have neither. So let's look at the graph first of all and find the critical points. The only critical point that we've got is right here at x is equal to 0. And it's between the second and the third interval. And in this, it went from increasing to decreasing. So it's got to go up here, hit the critical point, and switch to decreasing. So back over here, you can look at it in there. So that just means this. If you go from here to here, between here and here, it goes from increasing to decreasing, which tells you by the first derivative test that you have to have a maximum right there. So again, it went from increasing, it changed to decreasing. If it was going up and now it's going down, that means that there must be a maximum. So a maximum at that critical point. So at x is equal to 0. So again, back on the graph, we'll actually go ahead and write that down. We now know that this critical point, there's a horizontal tangent there, but you also know that on the graph, it's going to be a maximum. So the first derivative is giving you one more piece of information. So now, with each one, we build up the stuff, but we're going to wait to the very last step to sketch the graph. So back to the worksheet. Now the next thing, you use the same, or if you use the critical points, to find out where it's increasing or decreasing, you use inflection points to find out where it's concave up or concave down. First of all, you've got to find the inflection points. Now, you might remember the inflection points occur where either the first derivative is equal to 0, or the second derivative is equal to 0, or the second derivative is undefined. Now, these are going to be possible inflection points. It won't be an inflection point unless the concavity actually changes. So let's first of all go ahead and set the second derivative equal to 0, solve for x, and that'll give us the location of any inflection points. So again, let's first of all just write down what that second derivative was. The second derivative was, and we'll go up to here, 18x squared plus 12 divided by 8x x squared minus 2 cubed, and that's going to be the second derivative. So I'll just write that down just where we've got it handy. Okay, so this is going to be 18x squared plus 12 divided by x squared minus 2 cubed. Okay, so that is the second derivative. Now, set the second derivative equal to 0. You're going to set this thing equal to 0 and solve for x. Again, you've got a fraction equal to 0. The only way a fraction can be equal to 0 is if the numerator is equal to 0. So forget about the denominator and just look at the numerator. So that gives you 18x squared plus 12 has to be equal to 0. So that's going to give you 18x squared is a negative 12, which gives you x squared is negative 12 over 18. But again, nothing squared can ever be negative, so this is never true. So sometimes it'll actually be equal to a value, but in this case, it's never true. So what this means is there are no more inflection points. So there are no additional IPs. So normally we would go back to the graph and mark a point on the graph, but in this case we have no more inflection points. So when we go to the graph, there's nothing really to mark on the graph. But this step also says find the corresponding intervals on the graph. Now let's go to the graph. Now at first you might look at this. Second derivative information is going to go at the bottom. But since there's no inflection points, you might say, well, there's no intervals. But remember, this is where the asymptotes come in. Just like you treated an asymptote behaves as if it's a critical point, an asymptote can also behave as if it's an inflection point. So it's possible that the function could change concavity wherever you have an asymptote. So you have to treat the asymptotes as if they behave as if they're inflection points. So that is actually going to give you some intervals. So what we'll do, we'll have a red interval, and just like we did in that first example, we'll go ahead and put all the second derivative stuff in red here at the bottom. So that's going to give us an interval to this asymptote. Then it's going to go across to this asymptote. There's another interval right there. And finally, from here off to a positive infinity, there'll be another interval out here. So again, even though you didn't have specifically an inflection point, you wind up with 3 intervals because the asymptotes behave as if they were inflection points. So now the question is, in each of these intervals, is it concave up or concave down? So you've got 3 intervals. Let's go back and take a look at that. So back to the sheet. So we've got the intervals marked on the graph. So you go to the next step. And the next step says this. Pick a test point inside each interval and find out if the second derivative is positive or negative. Now, you might remember, if the second derivative is positive, the function's concave up. Wherever the second derivative is negative, the function's concave down. So we want to pick a convenient test point inside each interval, evaluate the second derivative, and find out what's going on in that. So let's go back to the graph and pick these values. Now again, pick anything convenient in this interval. So what I'm going to pick, and usually an integer is the easiest thing to work with. So in this first interval, I'm going to pick -2. In the second interval, I can pick any x value I want. I'm going to pick 0. That's a very easy one to work with. And finally, in the third interval, I'll pick 2. So I'm going to evaluate the second derivative at 2, 0, and 2 to find out whether it's concave up or down. So back to the worksheet. So let's go ahead and write those down. So first of all, you want to evaluate the second derivative at -2. You want to evaluate the second derivative at 0. These are our test points. And you want to evaluate the second derivative at +2. And again, all we're concerned about is it positive or negative? So we'll plug it in, and we'll actually plug it into this second thing right here. So everywhere we've got an x, we'll plug in a -2. So this is going to be 18 times a -2 squared plus 12 divided by, this would be a -2 squared minus 2. This time, though, it's going to be cubed. Okay. So what that's going to give you now, in the numerator, we'll look at it. We really want to know just positive or negative. Now, in the numerator, when you square this, it's going to be positive. Everything else is positive, so the numerator is actually going to be positive. Now, because this is cubed, it might turn out to be negative, so I have to take a look at this a little bit more carefully. -2 squared would be 4. This is going to be like having 4 minus 2 cubed, which would be 2 cubed, which would be positive. So you wind up with a positive divided by a positive, which tells you that the whole thing is positive, and therefore it is concave up. We'll put a CU. Okay, now what's going on this next one? Plug in a 0. 18 times 0 squared plus 12. All divided by, this is going to be 0 squared minus 2 cubed. Okay, that's going to go to 0. You'll have a 12 that's going to be positive in the numerator. Now this time you'll actually wind up with a -2 cubed. So a -2 cubed would be a negative, and that's going to wind up with a positive divided by a negative. This entire thing would be negative, which tells you in the second interval it's going to be concave down. Again, don't be in a rush on these problems. They just take a while to go through. You have to be slow and steady to get through these things. So finally, let's see what's going on in the third interval. 18 times 2 squared plus 12 divided by, and this is going to be 2 squared minus 2, the whole thing cubed. So in the numerator, when you square that, everything in the numerator is positive. And again, you'll wind up with a 4 minus 2 cubed in the denominator, which would be positive. It's going to be 2 cubed, which would be a positive 8, but we just care about the positive. Positive divided by a positive is a positive. The whole thing is concave up. So now we know what's going on, the concavity in each of the intervals, and let's go ahead and write these, concave up, concave down, and concave up on the graph. So back to the graph, and again, my suggestion is everything in the first derivative is in blue, everything involving the second derivative is in red. So we found out that this was concave up in this interval. It is concave down in this interval, and it switches back to concave up in this interval. So you're learning a lot about your graph. So let's go back to the worksheet and find the remaining stuff. Now, the last thing is the end behavior of the graph. What happens is you go way off to the right or way off to the left. And in effect, we really always did this back in the first step. Let's go way back up and take a look up here. in the very first step, we actually found, as part of finding the horizontal asymptotes, we found these limits, and it turned out to be y is equal to 1. But just to be consistent, we'll run through it one more time here. So what I want to do is to find it as it goes way off here. So the original function was x squared. Oops, put it in black here again, just to be consistent. So I've got x squared plus 1 divided by x squared plus 2, or minus 2, sorry. So minus 2. And again, the coefficients here are 1 and 1 because the power in the numerator is the same as the power in the denominator. That should be a 2. Then the limit is just the ratio of the coefficients, which is 1 over 1, which is 1. So this, as a horizontal asymptote, is y is equal to 1. And you can do the same thing here. When you plug it in, you'll wind up with a 1 over 1. I'll leave this other stuff out. And it's going to, following the same logic, it's going to be y is equal to 1. So again, back to our graph. And that's really no new information on that. We have a horizontal asymptote, and the graph's going to have to approach that. Okay, after all this work, we're finally ready to sketch the graph. So let's go back, and this is going to be exactly the way we did it in that first video. You look at each interval. You've got 4 intervals to look at here. Now, the idea is it has to satisfy the requirements of the top, and it has to satisfy the requirements of the bottom. So in this interval, it has to be increasing and concave up. Now, it can't be down here, because if it was down here, suppose that we decide the graph looks something like this, it was down here. It can't be this one, because this graph is decreasing, and it's also concave down. So it can't possibly look like that. It has to go, and we'll move right back up here. The only way this thing can satisfy it is if it did this, is if it comes in from here, and it has to be concave up. So it's got to come in something like this, remaining concave up and approach these 2 asymptotes. It has to look kind of like that. Now, I always put these little hairs on my graphs to indicate concavity. So if it's concave up, I put the little hairs on the top side of the graph. And this just kind of helps me visualize the whole concave up thing. So if it's concave up, the graph has to be curving up as you go this way. So that is increasing and concave up. So now look at the second interval. In the second interval, it has to be increasing, but concave down. And also, it has to have a horizontal tangent here. So the graph has to level off and have a horizontal tangent right there. And the only way it could and it also has to hit a maximum right here. So the only way it can satisfy all those conditions is if it looked like this. It goes through here, has a horizontal tangent here, and then it's actually increasing like this. It has to be increasing and also concave down. So it's going to approach that asymptote, and I'll put these little hairs again, this time on the bottom of the graph, to indicate the concavity is concave down. So it's concave down all the way through to right there. So that takes care of the second interval. Now in the third interval, it switches from, it was increasing, it's going to switch to decreasing, but it's still concave down. So it has to leave right here with a horizontal tangent, be concave down and go like this, and it's going to approach, but not touch that asymptote right there. But again, still concave down, so I'll put the little hairs on the bottom of the graph, just to indicate concavity. So it goes like that. Now the final thing, in the final interval, it has to be decreasing and concave up. Well, it can't be down here, because if it was down here and it looked like this thing would be increasing, and also it would be concave down. So the only way it can satisfy the requirements to be decreasing, concave up, and approach this asymptote is if it looks something like this. It's going to start from here, and it has to wind up looking something kind of like that right there. So it's got to be decreasing and concave up. Now I'm going to go ahead and put concave up. So this time I'll put the little hairs on the top of the graph. Above, it looks like that. So that should be a pretty good idea. Now the final thing is the end behavior. Let's go back to our final thing. What we said is, if you go way off to the left, this thing is going to be approaching the line y is equal to 1. If you go way off to the right, it's going to be approaching the line y is equal to 1. And sure enough, as you can tell, this thing goes down, and it's going to be, arrowhead's going to be approaching that, and it's going to be approaching that. So this little green thing right here actually is the line y is equal to 1. So the final graph should look something like that by the time you get it all sketched. Now, just like before, the next question is how good an estimate do we have here? How good is this graph? So let's go ahead and put the computer-generated graph on top of this, and you'll see that we're going to have a pretty reasonable graph here. So let's turn on this is going to be in red. This will be the computer-generated graph. So if you did this thing, it actually looks like this, and you can tell our little black sketch graph is pretty close to the red computer graph. As a matter of fact, let's go ahead and turn off the black graph. We can see exactly what it looked like. So everything fits. You have critical points, maximum here, concave up and concave down where it's supposed to be, switches from increasing to decreasing at certain points. All the increasing and decreasing matches up. Let's go ahead and turn ours back on again. So when you turn it back on, you can see that you actually get a reasonably accurate graph. Now, one final thing, just to see the effect of the first derivative and second derivative, let's go ahead and turn the red graph off, and let's turn off the second derivative information. So if we turned off the second derivative information and just look at the first derivative information, you can see if you combine the first derivative information with the asymptotes, it divides it up into intervals where it's increasing and decreasing. The blue information tells you about increasing and decreasing. Now, let's go ahead and turn off this first derivative stuff, and you'll see that the red information actually divides it up into intervals where it concave up or concave down. But again, it's the red working in combination with the green that allows you to do that. So the asymptotes also function as inflection points. So let's put everything back on there together now where you can see it all. So again, when you sketch these, my suggestion is I kind of use colors on these. I put all the first derivative information in blue at the top of the graph. I put all the second derivative information in red at the bottom of the graph. And then when I go through the worksheet, I'll just mark stuff on. And then finally, any asymptotes, I'll put in green just to divide it up and like that. So if you follow these steps, this is just an example of how to sketch a graph with asymptotes. And just remember, the asymptotes, although a critical point and an inflection point can't strictly exist at an asymptote, the asymptote, if you treat it in your graph, it actually behaves as if it could be an inflection point or a critical point. In other words, the increasing and decreasing can change and the concavity can change. So there's an example of a function with asymptotes. And you can tell this is kind of a long process, but if you just stay slow and steady, and the end result is, and we'll turn it on the red one more time, you'll get actually a pretty accurate graph by the time you get finished. So hopefully this will give you a little bit of an idea of how to sketch graphs with functions that involve asymptotes.